Hi. So far we have discussed about cut sets. Okay, so we'll now analyze some more properties of cut sets. So before that, what do you mean by cut set? Okay, so cut set in a connected graph is a set of edges whose removal disconnects the graph. Okay, whose removal disconnects the graph, and no proper subset of those edges will disconnect the graph. Okay, for example, if your graph is like this, okay, and suppose I am disconnecting these four edges, you can see that the graph will be disconnected into two like this. Or suppose my graph is like this again here, okay, and if I'm deleting these edges, my graph will be disconnected into two. Okay, so you can see that the vertices are not being deleted, only the edges are being deleted in a cut set. Okay, so this is the idea here. Okay, so let us now discuss the concept of fundamental cut sets. Okay, so fundamental cut sets are very similar to a concept which we have studied earlier, which is called fundamental circuits. Okay, so I hope you remember what do you mean by fundamental circuits. Okay, so fundamental circuits was always defined in relation to a spanning tree. Okay, suppose you had a graph G like this, suppose you have a graph G like this. Okay, take a spanning tree of that graph. So what's a spanning tree? A spanning tree is basically a subgraph, which is a tree which contains all the vertices. Okay, so spanning tree of this graph is basically, this is one spanning tree. Okay, now if I add one edge to this spanning tree, what will happen? I'll be getting exactly one circuit. Okay, or if I'm adding another edge like this, I'll be getting another circuit. Or if I'm adding another edge, we can see that I'll be getting one circuit. Okay, so a circuit obtained by adding exactly one edge to a spanning tree is called a fundamental circuit, or in other words, exactly one chord. Okay, I hope you know the meaning of branches and chords in a spanning tree. What are branches? The edges of the spanning tree are called its branches. The other edges are called the chords. Okay, so we are adding another edge to the spanning tree. So as a circuit obtained by adding exactly one chord to the spanning tree is called a fundamental circuit. So similarly, you will have a concept of fundamental cut set. Okay, so as I told you, suppose your graph is like this. Okay, and I'm taking a spanning tree like this. Okay, if I add one chord here, this is the chord here. Okay, this circuit obtained by adding exactly one chord to the spanning tree is called, so this was my spanning tree, is called the fundamental circuit. Okay, so similarly we have a concept of fundamental cut set. So what is it? So basically, suppose we are taking this graph again G here. Okay, and you take a spanning tree of this graph. Okay, suppose again I'm taking the spanning tree as this one. Okay, now take a cut set of this spanning tree. I am going to take a cut set. So suppose I'm just deleting that edge. So what will happen? This is my spanning tree T here. This is my graph G here. So when I delete that edge, what will happen? The T will be disconnected into two components. One V1 having edges V1, having vertices V1 and V2. Okay, now look at the partition, the original graph which produces the same vertices. Okay, so look at the cut sets in the original graph which produces the same partition of the vertices. Okay, so in the same original graph, if I want a partition of the vertices like this into two. Okay, so for that, which all edges should I delete? I should delete this edge, this edge, this edge, this edge. So this is a cut set of the original graph. Okay, so if you look at that cut set, you can see that this cut set contain this branch of the tree. Okay, this cut set contained this branch of the spanning tree, or this contained exactly one branch of a spanning tree. Okay, so a cut set containing exactly one branch of a spanning tree is called a fundamental cut set. A cut set containing exactly one branch of a spanning tree is called a fundamental cut set. Okay, for example, so that means always a fundamental circuit is circuit, and also a fundamental cut set is always defined with respect to a given spanning tree. When your spanning tree changes, your fundamental circuits as well as your fundamental cut sets will change. So fundamental circuit is basically a circuit obtained by adding exactly one chord to a spanning tree, and a fundamental cut set is obtained by adding is a fundamental cut set is a cut set containing exactly one branch of a spanning tree. So that is the idea. Okay, so we can see some fundamental cut sets here. So suppose I have a graph here like this, and I have a spanning tree which is drawn here with thick lines. For example, this is my spanning tree here. Okay, so this is my spanning tree. You can see this here. Okay, suppose I am deleting this edge. Okay, this edge is actually E here. I am deleting this edge. Okay, now that will partition the vertex set into two, this one and this one. Okay, now look back to the original graph in which I want to find a cut set which partitions the original graph into two like this. So what is that cut set? It is drawn here by dashed lines. So if I delete these edges, that is, if I delete the edges D, E and F, I will get the same partition. Okay, so this is called a cut set, and also it contains exactly one edge of the given spanning tree. So this is my fundamental cut set. Okay, so for the, it's basically fundamental cut set with respect to this spanning tree T. Okay, and also using this edge E. Okay, suppose I am taking another edge here. For example, I am taking the edge H here. Okay, so if I delete H in my original tree, what will I get? I will be getting this portion and also this portion of the vertices. Okay, now I want a cut set of the original graph which produces the same effect. So what is the cut set? It will simply your HGF. So HGF also produces the same partition of the vertex set into 2. So what will I get? So this means this is a fundamental cut set because it contains exactly one branch of the spanning tree. Okay, so your fundamental cut sets are always defined with respect to a given spanning tree, and for each edge you can create a unique fundamental cut set. For each edge you will be getting corresponding a fundamental cut set. Okay, so for each edge there is a uniquely determined fundamental cut set. Okay, so all the fundamental cut sets are actually marked here using the dashed lines. You can just verify it. Okay, so here is the example here. Suppose I want to find a cut set which contains only this C. What will I do? You have to just delete these edges here. So there, if I delete A, C and D, this graph will be disconnected. Only thing is that you will be getting only one vertex here, and all the other vertices will be the other set. Okay, so that is same. So this cut set, that is A, C, D, contains exactly one branch, and that is a fundamental cut set containing this C. Similarly, you can get another branch which contains this B only. What is that one? So this is your fundamental cut set which contains this B only, which is your A and B. Okay, so that will only contain this. So a cut set which contains exactly one branch of a spanning tree is called a fundamental cut set. So fundamental cut sets depend upon the spanning tree given. If your spanning tree is varying, your fundamental cut sets will be verified, and also they depend upon the edge taken or the branch taken. Okay, for each branch you will have a different fundamental cut set. Okay, so that is the idea of fundamental cut set here. Okay, I hope it is clear. So as I told, this is basically the definition of, so I can ask you to define a fundamental cut set with examples. Okay, so always they are defined with respect to a spanning tree, and for each branch you can have a different fundamental cut set. Okay, so next what we are going to do is that, next idea is, suppose you have some spanning trees, so suppose you have some cut sets in a graph, not a fundamental cut set, I'm just taking cut sets. So how to produce new cut sets? Okay, just like we have studied subgraphs, how to produce new subgraphs from a given graph, you had many operations further like union, intersection, ring sum, so many things were similar, deletion or difference, so many things were there. Okay, so similar to that, we will have some, suppose we have some cut sets of a graph, how to produce new cut sets. That is what we are going to discuss here. Okay, so that's a very important result. So the ring sum of any two cut sets in a graph is either a third cut set or an edge disjoint union of cut sets. So they are telling you that suppose you have two cut sets of, for example, S1 and S2, their ring sum will produce a new cut set or basically an edge disjoint union of cut sets. So it will be a collection of cut sets. So that is the idea. So before we proceed to that, I hope you remember what's a cut set, what's a ring sum, what is a ring sum. You studied this in operations in graphs. So what's a ring sum? Okay, so it's very simple idea. Suppose my graph is like, suppose my graph is like this, and suppose one subgraph is this, another subgraph is this. Okay, so this is your G1, this is your G2. What is ring sum of G1 and G2? It will contain the vertex set will be contain all the vertices which are in G1 and G2. Okay, so the vertex set will contain all the vertices which are in G1 and G2 first of all, and the edge set will only contain those edges which are in either of them but not both. Okay, so edges which are common to both the graph would not be present. For example, in the ring sum of G1 and G2 is basically all the vertices would be there. Okay, but this edge cannot be there, this edge cannot be there because it is common to both of them. So they will not be there, only this will be there. Okay, so the ring sum consists of those edges which are only present in one of the subgraphs. Okay, so it will not be present in both the subgraphs. That's the idea of a ring sum. Okay, so here they are telling you is that suppose you have two cut sets, it will have so many edges there. So you take the edges which are not common to both of them. Okay, remove the edges which are common to both of them. So the remaining set of edges will be a new cut set, or it will be a disjoint union or collection of cut sets. Disjoint union of cut sets. Okay, that's the idea here. Okay. So this is the definition of ring sum, which you have already taught you in what you say in your previous modules or something like that. So now we will proceed to this proof here. Okay, so we'll start this proof. Its proof is basically heavily geometrically based. So you need to draw a graph to understand this proof. So try to draw the graph with me to understand it better. Okay, suppose what I will do is that suppose I'll take a connected graph. So basically we are discussing only we have to discuss cut sets with respect to connected graphs. Okay, so suppose I have a connected graph here. I'll take two cut sets of this. So one cut set is S1, another cut set is S2. So S1, now suppose I'm taking it as this horizontally, I'm going to cut it. So horizontally I'm going to cut it means I'm just going to delete this edge, this edge, this edge, this edge, this edge and this edge. Okay, so the remaining would be simply only these two vertices would be remaining. So it actually partitions the vertex set into two like this. So it will partition the vertex set into two like this. Maybe I'll call it as my V1 and V2. That is one cut set. Similarly, the next cut set is basically I am going to delete horizontally like this. So I'll be deleting this edge, these edges and this one. So what will I get? I'll be getting the corresponding graph like this. So my vertex will be partitioned into two like this, V3 and V4. Okay, so I'll take two cut sets. One is your S1, another is your S2. One I am going to cut horizontally, another I am going to cut vertically. So I will be getting correspondingly your vertices vertex will be partitioned into two different components. So I'll call them V1, V2, V3, V4, etc. So I can also say that this V1 union V2 is equal to your entire vertex set, and similarly there is no intersection here. So V1 intersection V2 is simply 5. That is why they became two components. Similarly, you can have V3 union V4 will be V and V3 intersection V4 will be 5. Okay, so basically I have taken two cut sets. I am just discussing the effect of that cut sets only. Now, okay, so this is the idea. So this is a general graph here. So I showed you a simple graph. This is a general graph here where V1 contains so many vertices and edges here. V2 will have many vertices like this here. But I am just focusing only on the cut sets. That's why I have just shown the cut sets here. Okay, so first way I am going to divide it vertically. This is my S1 here. So when I divide it vertically, what will happen is this will be disconnected into two like this. Okay, so this is your, maybe I'll call it as V1, this will be called as V2. So I can say that V1 union V2 will get the whole vertices because we are only deleting the edges, we are not deleting the vertices. And similarly, V1 intersection V2 will be 5 because they are belong to different components. Okay, so that is the idea here. And similarly, next what I'll do is that for S2, I'll cut it horizontally. So this is my S2 here. And similarly, there will be two different partitions produced now, that is your V3 and V4. And the same properties as before, V3 union V4 will be your V and V3 intersection V4 will be 5. Okay, so that is the idea. Now let us take the ring sum of these two, what you say, cut vertices. Let us take the ring sum of these two cut sets and see what you're going to get. Okay, so I'm looking at these two vertices here, two cut sets here, and let's see the ring sum. Can you tell me what would be the ring sum of these two? S1 and S2. What will be the ring sum of S1 and S2? Can you tell me? So it will contain what? It will not contain common edges. Only the edges which are not common will be contained. So it will not contain, this edge will not be there, right? This edge will not be there. Only those edges which are not common will be present. So what will be my ring sum here? So essentially my ring sum will consist of this, this, this and this. So that will be my ring sum, right? So the ring sum will contain only those edges which are not common to both the cut sets. Okay, so basically this is my ring sum. Or in other words, suppose my example, earlier example, simple example was like this one. Okay, so this was my earlier example, and my first S1 was like this one here, and my S2 was like this one here. If I draw it like this, okay. Now what is the ring sum here? My ring sum just consists of this one here, these edges here. Okay, now I have to show that this ring sum is basically a cut set, or it's a disjoint union of cut sets. That means basically the ring sum will disconnect the graph. So will the ring sum disconnect the graph? Okay, if I remove these edges, will it disconnect the graph? Of course, it will. The graph, if I remove these edges, what will happen? My graph will become like this. Okay, you can see that it is disconnected. Okay, here there is no intersection. This is basically two edges which are not crossing over. So basically they are not intersecting here. There is no vertex here. This is basically two different edges only. Okay, so you can see that if you remove the ring sum of edges in this simple graph, the graphs will be disconnected. Okay, so that is the idea which you are going to use. So when you have to show, if you want to show that this S1 ring sum S2 disconnects the graph, you have to bring a partition of your graph into two vertex sets maybe already I have taken V1, V2, V3, V4, so I'll take to have to divide it into two vertex set V5 and V6. Okay, we have to show that this will partition the graph into two distinct vertex sets V5 and V6. Okay, so that is what we are going to do here. Okay, so try to understand what is S1, what is S2, and what is the ring sum of S1 and S2. Look at that and see what effect happens when you remove this S1 and S2. Okay, that is the idea here. Okay, so basically to show that this rings, when you removal of this ring sum will disconnect the graph, so we need to partition the vertex set into two, one V5 and also a V6. So let us try to write it formally here. So what will I do that? So in order to write it formally, or in order to create that V5 and V6, what I'll do is that I'll try to understand this vertex sets or portions of the graph better. Okay, so if you look at this set of vertices here, okay, can you write this set of vertices in terms of our V1, V2, V3 or V4 in any of them? This set of vertices. You can see that this set of vertices is common to V3 and it's also common to V1. So can I say that represents basically V1 intersection V3? Okay, because it is common to both V1 and V3. Okay, so if you have understood that, what can you say about this set of this portion of the graph? You can see that it's common to both V3 and V2, so it's simply your V2 intersection V3. So similarly, you can label other edges also. You can say this is actually your V1 intersection V4 and this is actually your V2 intersection V4. Okay, so this is the idea here. Okay, now if you have understood this labeling here, okay, it's very simple thing. You're just taking the vertices which are common to S1, S2, V1, V2, V3 and V4 here, and we have labeled everything. Oh, no. Now look at our ring sum. What is your ring sum? Our ring sum is actually these edges here. Okay, our ring sum is actually these edges here. Now tell me, if you delete this ring sum, what will happen? This graph will be disconnected into two. Okay, graph will be disconnected into two. One is actually this portion, another is actually this portion, right? This graph will be disconnected into one is actually this portion and this. So I am calling this portion as simply my V5. I will call this portion as simply my V6. Okay, so when you delete the ring sum, the graph will be disconnected into. So actually we have to show that deletion of the ring sum disconnects the graph. So this is your idea here. From geometrical itself, we will understand how to write that one, how to write the V5. So when you delete that ring sum, you can see that it is disconnecting it into two parts. One part I am calling it as V5 and another part I am calling it as V6. So what is your V5? So V5 is actually your V1 intersection V4 union V2 intersection V3. So this part V1 intersection V4 union V2 intersection V3. Similarly, what is your V6? Your V6 is, looking in the graph, I can write it, that is simply V1 intersection V3 union V2 intersection V4. Okay, so that is other part here. Okay, so if you want, in set theoretical notation, it's not required for I'm telling you, suppose you're considering this V1, V2, etc., V3 as sets here. Okay, set only, and you are not considering this here. Suppose don't consider ring sum, just remove the ring sum edges. So your graph is like this. Okay, so your graph is basic. Suppose your graph is like this. Okay, now so your graph is like this. You can see that this portion, the thing which you have written here, that is actually your V5. Okay, so V5 I have written as V1 intersection V4 union V2 intersection V3. Okay, but that I can also write it as simply V1 ring sum V3 in set theoretic notation, not according to graph theory. I'm just telling set, just for understanding. I'm telling you it's not required for you, but just I'm giving a simple, what to say, observation. Okay, it's not required for you, but you can see that this can be written as actually V1 ring sum V3. Why is it so? I am just removing the common portion to both V1 and V3. This is the common portion. I am only taking the remaining ones. So I am just removing the common portions to V1 and V3. I am just only taking the remaining ones. So this can be written as simply V1 ring sum V3 if you want. It's not required for you, but just telling you as an observation. Similar this one also. This portion I am actually removing this common portion of V2 and V4. So this V6 can be written as so not V6 here. I am taking the other one here. So this one here, so I'm just removing this portion here. So that is actually your V2 ring sum V3. Okay, it's not required for you. You just need to write V5 and V6 in terms of these things only. This is just an observation which are made in text. It's not relevant to the proof here. Okay, just an observation only. Okay, so that's it. So we'll call this one, that is your V1 intersection V4, V2 intersection V3. This portion will be called my V5 and this portion will be called my V6. This portion will be called my V6. Okay, so that's the idea here. Okay, and you can see that the ring sum will, when you remove the rings edges in the ring sum, that is these edges, what will happen is that the graph will be disconnected into these two components. Okay, so you can see that removal of ring sum disconnects the graph into V5 and V6. So that is how we are going to end the proof. Okay, I hope it is clear. So it is clear how we have written these portions here. Okay, so this is basically not required for you. This is only a set theoretic notation. Its basic idea is that you are actually removing the common portion of V1 and V3 here. Okay, when you are writing V5, I am just removing this common portion. I am just taking only this portion here, and these edges are not considered. So they are only writing it in terms of set theoretic notation for the vertices. Now they are not considering the edges there. Okay, this is just for idea. This is only for information only. It's not required for it. Okay, so this much I hope it is clear. Okay, so now you can see that. So if this is my graph now, okay, this is my V5, this is my V6, and they are being connected by these ring sum edges. Okay, so once I delete these ring sum edges, I can see that it will disconnect the graph. Okay, and the property of this ring sum edges is that they are the only edges which are connecting this V5 and V6. So these are the only edges which are connecting the V5 and V6. Okay, these are the only edges which are, no other edge will connect this V5 and V6. Why? Because we have obtained this ring sum from your cut set S1 and S2. Okay, so removal of S1 will disconnect all the two graphs. Removal of S2 also will disconnect the graph into two. Okay, so all the edges which will disconnect the graph are actually accounted in S1 and S2. Okay, so if there are any other edges connecting this V5 and V6, obviously they should have come to this S1 or S2. Okay, suppose there was an edge like this which connects this V5 and V6, that means it should have occurred either in S1 or S2. Okay, so there are no extra edges which will connect V5 and V6 because all the edges which are connecting this V5 and V6 are covered by this S1 ring sum S2, because the S1 and S2 are cut sets. So all the connections are accounted in S1 or S2 itself. Okay, so there are no edges connecting this V5 and V6. Okay, because V5 and V6 are defined in terms of the partitions created by S1 and S2. That's the idea. Okay, so that means once you delete this ring sum edges, what will happen is that your graph will be disconnected into just V5 and V6. Okay, so when you delete this partition edges, your graph will be disconnected into V5 and V6, and also you can see that since you are deleting only the edges, your V5 union V6 will be your entire set, and V5 intersection V6 will be simply the null set. Okay, because there are no edges in common, and also all the vertices are there, no edges are there in common. So that means basically S1 ring sum S2 disconnects the graph. S1 ring sum S2 will disconnect the graph. That's the idea. Okay, now I can, so can I say it's a cut set? Okay, it will be a cut set. So it will be a cut set provided your V5 and V6 are connected components. It will be a cut set provided your V5 and V6 are connected components. Why is it so? What's a cut set? Cut set is a small basically a cut set is the smallest set which will, or the minimal set which will disconnect the graph. A cut set is a minimal set which will disconnect the graph. Is it clear? Okay, so this S1 ring sum S2 is the only set of edges which are connecting this V5 and V6. S1 ring sum S2 is the only set of edges which are connecting this V5 and V6. Okay, so when you remove S1 and S2, all the connections between V5 and V6 will be severed, and you will be getting two distinct components. One is V5 and V6. Okay, so now if V5 is not, suppose V5 is not connected, suppose V5 was disconnected. Okay, so suppose your V5 which has to be, suppose it was disconnected like this. Suppose it is like this here. Okay, suppose it is like this. What does that mean? That means actually your S1 ring sum S2 had some extra edges which created a disconnection in V5. Okay, so this S1 ring sum S2 contains all the connections between V5 and V6. So when you delete anyway S1 ring sum S2, all the connections between V5 and V6 will be removed, and that means this we are getting two different components, that is V5 and V6. Okay, now suppose your V5 is again disconnected. Suppose when you remove S1 ring sum S2, your V5 was disconnected. Okay, earlier the graph is connected only. So when you're actually removing only S1 ring sum S2 here. Suppose in that process, apart from V5 and V6, a new component has been created. Suppose V5 has been disconnected into two. What does that mean? That means there are some edges in the ring sum of S1 and S2 which disconnects V5 also. Okay, there were some edges in the component which disconnects V5 also. That means S1 ring sum S2 is not a minimal set and hence it cannot be a cut set. Okay, so this happens only if either your V5 or V6 is again disconnected. Okay, suppose your V5 and V6 are not disconnected, that means removal of S1 and S2 will disconnect the graph into two, V5 and V6. And suppose V5 and V6 are connected components, that means S1 ring sum S2 is the minimal set which can disconnect the graph into V5 and V6. Okay, so earlier your graph was like this. Okay, so only when you delete these two or delete these ring sum edges can this graph be disconnected. So only the removal of S1 ring sum S2 can disconnect the graph into V5 and V6. So it's the minimal set which will do this. So that means S1 ring sum S2 is a cut set. Okay, so when will it not be a cut set? It will not be a cut set in the extreme case in which suppose this V5 itself has been disconnected or if your V6 itself has been disconnected. So how will that happen? That will happen if there are some extra edges which will disconnect V5 in the S1 ring sum S2. Okay, in that case, this will not be a minimal one. So it will be disconnected only if your V5 S1 ring sum S2 will contain some extra edges which can cause further disconnections in V5. Okay, in that case, S1 ring sum S2 will be not be a minimal set. Okay, so two possibilities are there. One possibility is S1 ring sum S2 is a cut set. In that case, that means your V1 and V2 will be, your V5 and V6 will be connected components. In that case, that means your S1 ring sum S2 is a proper cut set itself. In the extreme case in which suppose either of some of them, one of them is disconnected again. Suppose your V5 contains two components. That means some edges in this S1 ring sum S2 had disconnected this V5. Okay, some edges in this V5 had disconnected this V5. So how did that happen? So that means actually suppose your V5 is this, V5 your V6 is this, your V5 was this. Okay, this was my S1 ring sum S2 and again some edges may create some disconnection here. Okay, so what is the meaning of that? That means this S1 ring sum S2 will have S1 ring sum S2 will have some edges which will disconnect this V5 and V6 fully and also some edges which can disconnect this V5 also. So this S1 ring sum S2 will have some edges which will disconnect this V5 which will disconnect all the connections between V5 and V6 and also there can be some edges which can disconnect the connections of V5 also. Okay, that means this S1 ring sum S2 will be a disjoint union of cut sets. S1 ring sum union of will be disjoint union of cut sets. Why I am calling it as disjoint union? One cut set will be the one which will sever the connection between this V5 and V6 and other cut set will be a cut set which will be severing the connection in V5 itself. So you take these two together. So one cut set will disconnect this is the cut set here. One cut set will disconnect all the connections between V5 and V6. So it is one cut set and another cut set will actually causing a disconnection in V5. So we are getting two cut sets. Suppose again V6 also being disconnected, that means there will be a cut set in V6 as well. So if you take all these cut sets together, you will be getting a disjoint union of cut sets. That's only in the extreme case, but that possibility is also there. Okay, so I hope it is clear. So try to think this graph in terms of your geometrical approach, only then you'll understand this one. So anyway, when you remove S1 ring sum S2, what is happening is that your V5 and V6 will be disconnected. Okay, only possibility is maybe V5 could be disconnected further or maybe V6 could also be disconnected further. Okay, so in that case S1 ring sum S2 will be not a cut set, it will be a collection of union of maybe in proper way it is a disjoint union of cut sets. One cut set will be accorded for disconnecting V5 and V6, another will be accorded for disconnecting this V5. That's the idea. Okay, so that's an extreme case. I'll give you an illustration also where this sort of situation can also happen. Okay, so that is the proof here. Okay, so what have you done here? We took two cut sets, S1 and S2. One was vertically, one was horizontally. Okay, and we look at the what do you say? We looked at their partitions. Okay, then we looked at these sets here. We took the intersection of these set vertices here, and we looked at the ring sum and looked at what the ring sum was doing here. The ring sum is actually disconnecting the graph. So how to bring a partition of the vertices, so that we have written by writing this diagonal portion as V5 and V6, and rest we have done similarly. Okay, so please go through the proof once again and try to convince yourself of the results. If you have any doubts, you can ask in the chat box, or you can also message me. Okay, now let us look at the illustrations of also here. Okay, so let us look at the illustration here. So in this graph, let us look at some cut sets. So suppose first I am taking this D, E and F. So my cut set is D, E and F. Suppose my other cut set is this F, G and H. Okay, so these are two cut sets, and let us look at a ring sum of them. What is the ring sum of them? It will contain simply D, E, G, H. D, E, G, H. So what will happen if I delete these edges? You can see that the graph is being disconnected into two. Your V4 will be separate and others will be separate. So this is a new cut set. Okay, and you can see that no other proper subset can disconnect the graph, because even if you delete the D, E and G, still the graph will be connected. So no proper subset of this can disconnect the graph. So it's a cut set there. Okay, that is one idea. Okay, similarly you can go for another example, AB and BCF. That is, I am taking this AB and also I am taking this BCF. I am just deleting this BCF. What will happen? So I will be getting ACEF. What is ACEF? ACEF is actually this one. So if you delete this portion, you will be getting this one and also this one at two. So it's basically two different sets. So that's also a cut set. So your ring sum produces two cut sets. Okay, and again another case. So you are taking DEGH. So I'm taking this one DEGH, and also I'm taking FGK. I'm taking this one F, G and K. So when I take ring sum, what will I get? I'll be getting remove the common ones. That is simply D, E, F, H, K. So what is D, F, H, K? D, E, F, H, K. D, E, F, H, K. So this is the portion here. So that many edges are not actually required to disconnect the graph, because you can, if you just delete D, E, F itself, the graph will be disconnected. Okay, so this will not become, it is not a cut, this alone will not be a cut set, because it's too many edges are there. That's the extreme case I told you about. Okay, so in that case you can see that it is actually a connection of DEF union HK. So one set to disconnect this V1 and V2, and another set to disconnect this V2 itself. That's the idea here. So DEF union HK. So it's an edge disjoint. So one set of edges to disconnect the graph into two, as I told you, V5 and V6, and another set of edges to actually disconnect the V6 itself. Okay, so that is your HK. So this case can also happen. Okay, so that's it. I hope it is clear. Please go through the proof again. Now go through the proof once again, so that you will understand the concepts once again. So if you have any doubts, you can ask. Okay, thank you.